The motion planning will be, it will be quite like, not that I plan to do everything else, particularly tricky. I think people that know me a bit more not known for giving unreasonably hard tests, but first time always for everything. Motion planning, let's talk about what we discussed last meeting. To start with, our obstacle is nothing but our robot, is nothing but a single point, starting point over here, and we want to find a path from source to destination, and that avoids all the obstacles, and we said we need to somehow do a vertical decomposition. Now we have a bunch of trapezoids, no more than order n. Why? Because that's the number of the events that the line sweep go through. And as the line sweep go from one event to the next, then we are shooting rays up and down until you hit one of the other events in the status. And do remind yourself what is the status, because it will come back today on Thursday with respect to the visibility graph. The visibility graph is tools that we'll cover a bit later that will help us find not only a path, but the shortest path. It will cost in complexity and running time, but it will be the shortest path rather than just a path. This path is just whatever this set of trapezoids will give us. Anyway, we handled the case of trapezoids, and we asked what happens if my robot has a shape, convex shape, because the world would be a much nicer place if everything would be convex. So the robot is convex, each of the obstacles is convex as well. For the obstacle, it's not such a ridiculous assumption that the obstacles are convex, because if it's not convex, you can just triangulate them and create more triangles, and triangles are convex. And it doesn't really affect the complexity, as we will see. Why can't we rotate the robot and so on? We'll talk about more degrees of freedom later on. To start with, many interesting things happens even if the robot can only translate. We discussed the notion of the forbidden space, the set of position of the center of the robot. Remember, we had to pick some point in the robot and called it the origin, and now every other point in the plane corresponds to some translations. And a few of the translations cause the robot to intersect with one of the obstacles, a few are not, and we asked for one particular obstacle, and the robot the same all the time. What is the set of all translations that cause the robot to intersect with this particular obstacle, forgetting about other obstacles, just with this one? What are the set of forbidden position of the origin of the robot? And the answer was lying on the Minkovski sum, taking the robot and shift it around, but with a little caveat. Was the Minkovski sum on this, and this obstacle and this robot, and the Minkovski sum was defined as a pair of all points, one from here, one from here, like double loop of all of them, but as we'll see, for two convex polygons, actually linear time is all we need coming up. Now, so the Minkovski sum of two convex objects is always convex, and covered it more than once, just for convexity. Take any two points, you have it all in the PDF. Take any two points that belongs to the Minkovski sum, then where are they coming from? They're coming from two points, so point of the source and point of the object. From this point, point of the points, point of the object for the other extreme points, and then you're just generating parameterized everything by lambda, like the time that lambda would be the time that the fly is between the two endpoints of this segment. The usual trick, nothing really clever in it. We talked about taking the robot and looking at the minus of the robot, which was take every point x, y, and transform it as a point minus x minus y. Like flip, and another flip to this direction. Okay. And the forbidden region of the one particular obstacle in the robot, we proved that it is the Minkovski sum of the obstacle plus the minus robot. Take the robot and reflect it and then takes the Minkovski sum. Okay, everybody is happy so far? That was what we discussed earlier. I want to speak a bit more about extreme points. We had extreme points in several homeworks. We had extreme points in linear programming. We played in the homework about having a data structure that take a set of points and prepare it for extreme points question. I'll give you a direction. Here's a set of points, and I will give you a direction, D, and you'll have to give me in return what is the extreme points in direction D. In other words, look at the point D, look at the line that is orthogonal to D, and as you're moving the line parallel to itself, always orthogonal to D, but as much to the right as possible, what is the last point that it intersects. That was in the direction of D, and if the other extreme points in the same direction, would be, of course, take the minus D. That's what we essentially used when we proved that the optimum of the linear programming always happens in a vertex. We decided about the cost of banana, cost of orange, that determines the orientation, the direction of the budget line, and then slowly increase the budget until it starts including one of the points in the query. Points in the feasible region, sorry. If I have a set of given points and I will ask, prepare a data structure, it sounds much more fancy than it actually is. Prepare a data structure such that when I'll give you a direction, you can tell me what is the extreme point in this direction. The answer is very easy. Compute the convex hull, the extreme points no matter which direction it will be. It will be a vertex of the convex hull. And now, for every direction, in logarithmic time, after the vertices of the convex hull, in logarithmic time, I'll give you D, you'll tell me what is the vertex that is most extreme in the direction of D. Formally, we say that a point P over here, does it think? We say that some point P among a shape Q, not necessarily interplane, not necessarily connected, disconnected, a lot of points, contiguous, whichever is Q, is extreme points in some direction D. D is a vector, non-zero. It doesn't make sense if it's zero. If look at this point P, my dot product D, the vector D, it's the maximum that you can get when you're trying a lot of other points in Q. Just a fancy way to say, once I decided about D, then every point has a cost. Like the D, the dot product would be take this point that specify how many bananas, how many oranges, multiply by the cost of banana and the cost of oranges. That will be the overall the overall cost of what you're going to eat today. And now you're asking what is a diet that is the most expensive or what is a diet that is the least expensive. What is the 3 points in this direction? If you change the ratio between the cost of banana, cost of oranges, D will rotate, of course. The length of D is meaningless. It doesn't affect if a point is extreme in this direction or not. Cool with everybody what is extreme? If D happens to be 1, 0, unit vector in this direction, it will just be the rightmost point, or a rightmost point. It's not necessarily be unique. Despite the misleading connotation maybe of the name, this extreme points is not necessarily unique. If I have in my polygon an edge E, and D is 0 and -1, pointing downward, then I'm just looking for the lowermost point / point. And that's useful. So, and in a few proofs that are coming, I'll ask you to think about the sets of all directions. Every vector D is like a unit vector in the set of circle. If you're putting the 0, 0 at origin and make it a unit circle, then every vector D, you can specify at which direction it is. And of course, for every such direction, I can ask what is the extreme point of my region in this direction. And I think that you guys guessing where it is going for. Here is my shape. Here is my shape. This is the Minkovski sum of this creature and this creature. These are the two polygons of the Minkovski sum. We saw it create this shape. What creates the rightmost point? The rightmost point is created, well, Minkovski sum is a sum of any point here plus any point from here. And you're running over all the sums, but now I'm helping you calculate. How do I find the rightmost point? I'll take the rightmost point in green and add to it the rightmost point of the triangle in blue. And that would be true for any direction, right? I'm looking for the maximum of a point in the Minkovski sum, that is P in P and R in the robot. Look at all the pairs of points P and R, one in the obstacle, one in the robot. Multiply them, all of them, by D, and we're asking which point will bring it to the maximum value. Surprise, surprise, to get the maximum value, you can look at this product, say this is the product of P dot product D and the product of R dot product D. And to get the maximum, I will just take the maximum that I'm getting from P dot R, P dot product D, all the points in the obstacle. What do I mean? If D points to the right, then take the rightmost point of P and add to it the rightmost point in the robot. So it's just a formal proof that that's true, even if my right is actually, I tilted to the right, and then what used to be my right is actually in some other direction in the circle of all directions. So now you can, I think that you knew already, but it helps us understand what are the edges and vertices of the Minkovski sum. To create the Minkovski sum efficiently, what I'm going to do is slowly rotating the set of directions. Slowly rotating the set of directions. Now, for one particular direction, it's possible that I have only a unique extreme point in this direction, but a lot of times I'll have an edge which suggests a lot of extreme points in this direction. What does it mean? That in the Minkovski sum, I will have an edge. Every time that again, you're rotating around, circling around all the possible directions from 0 to pi, 0 to 360. And for each direction, you want to say, what is the extreme point of the Minkovski sum? Well, I'll find what is the extreme point in this polygon. I'll find what is the extreme point in this direction from this polygon. As I'm rotating my set of directions, what can happen? Either I am moving from one extreme point to another on the green. I'm just thinking about the green, and in the green I'm asking, what is the extreme point? Well, if it's D points to my right, it's an edge. As D increases, it will be the vertex, the corner of the green. We'll keep rotating until it will be another edge, keep rotating. And it will be this vertex and so on. And you're doing this full sweep. Simultaneously, as you're doing the sweep here, you're also doing the sweep in the other polygon. Two parallel lines that are both rotating together. I could have done animation, and the two parallel lines rotating together, and every time that you hit an edge of either of them, then it creates an edge of the Minkovski sum of these both these creatures. Since each polygon, the orientation of its edges are sorted, that it's convex, the same goes for this one. Then, as I'm rotating my two lines, one here and one here, asking what is the extreme point, how many events do I have, the number of edges, either in P or in Q. Either in P or in R. So that's just a linear algorithm. Yeah.
Is the observation on this slide here, is that only true if E and R are convex, or is that general?
That would be for every shape. No, there's nothing to do with that's for any set of points. Could be. Yeah, it could be completely discrete set. But the issue is computing it in linear time. That's hard. Now, let's wake you up a bit. I have two polygons. My polygon here is just I need to make it a polygon, so I'll just make this teeth of the cone very thin. So think about it as a polygon. It doesn't really matter. And it has n teeth, kind of spread apart. Q is similar, except that now my teeth are much smaller. And my question is, what is the complexity of the Minkovski sum of P Minkovski sum of Q, in this case. Complexity is how many vertices, how many faces, how many edges. Once you bound one of them, you bounded the rest. Does it look at all?
I guess I'm not sure what P and Q is. Yeah, I'm not sure.
So they are both common. It's just all. So it's a set of points. So all the blue points, that will be one common.
Oh.
And P will be another common. And each one has n teeth in it, like n segments on it. When I'm computing Minkovski sum, I don't care if it's common, if it's set of points or connected or not. Minkovski sum is still defined. So this has n teeth, that's one teeth, one tooth, one. The same goes here. But the teeth over here are very close together. And of course, Minkovski sum depending when I put the origin, but depending weakly, I just moved a bit if I moved the origin. can go back a few slides just to review a bit insight to how did we compute the Minkovski sum over here. We took one shape and slide it across the other shape. The origin of Q, and I slide it, and
is it just 2n?
I just n over there.
N squared.
N squared because it looks like
N keys on
I'm taking it and sliding it over here. So at some point my comb will get all the way to where its origin is mapped to here. So all the n teeth are sticking out over here. And similarly, the same teeth will be sticking out over here. So the complexity is at least omega of n squared. Everybody understand? How did I generate all these teeth? Great. This is the most I can do. Yeah.
Why is there no teeth? Like, why are there gaps? Like, you have sort of those 4 teeth, and then you have the gap, and you have another 4 teeth.
I take a copy of it. I mean, I create this Cartesian product. Every point here from every point here, but this little algorithm said that I can take the polygon, but it's common polygon, put ink on it, and let it slide across all the points of the other polygon. And every point that is painted, that my teeth moved into, I left as marked. So that gives us wizards. Yeah, stay with us, please. Make sense to everybody? Excellent. Is this the worst I can do? Like, can I create a polygon with complexity which is a bit higher? I'll give you a hint. Let's take this polygon and let's add to it a few multis. So now my comb looks like this, which you still have no clue why it didn't really affect what has happened here if Q contains both this and this. But now I'll ask, go back to P. And let's have P also go all the way to, and my distances are not exactly proportional, but let's have P also contain this part. This is definitely not connected. That is, when I swing this polygon all the way to here, it will have what happened to all these red teeth. They will start into each one of these guys, which I can do more than once, just the mirror image of this part once again. So each teeth in this twisted comb will create a set of n squared many teeth. These are the copy of this creature into this. So let's think about it. We have a set of n squared vertical teeth and n squared horizontal teeth, and each horizontal meets any vertical. So two non-convex polygon could create a region with omega so the difference is now I forget the convexity. Asking you how complicated is the region of the free space of this very non-strange robot. And to ask what is the free space, I'll ask how many vertices do I have moving between the free space, or not the free space of the translation, or how many intersection points do they have? We'll talk about it a bit more today. But how many intersections? Well, I created n squared horizontal teeth. N square vertical teeth, those are the blue. I'll also have n square horizontal. By taking this part of the cone and let it slash back and forth, back and forth. I mean, these things are not exactly in proportion. I'm taking it more to the right and let it stop. Back and forth, back and forth. So what should I replace this question mark? So what should I replace the question mark with? What should the question mark be replaced with? You or anybody else? How many holes can I generate? Yeah. So this will be R to n to the 4. So convexity really helps us here. Where two convex polygons have together n vertices without convexity and without any assumption about having the data realistic. The Minkovski is like a factory for really complicated chips. But there is a whole stream of research that talks about what is realistic and what is non-realistic as an input. Okay, let's talk about the algorithm so far. Before we walk further in improving it, I have a set of obstacles. Set of obstacles, non-intersecting polygons. I have a robot R and some point S, some source and destination. I'm trying to find a path from S to T. Different from the algorithms that we saw earlier, that my robot is not a point. What do? I compute this, the forbidden region of each obstacle individually. Ci is the obstacle Pi, Minkovski sum is minus R. I'm doing it in linear time, the algorithms that I just showed you before, kind of sweeping with both sides, with this line generating all the edges as I go around. Okay, that was each obstacle separately. Now, I started from a set of obstacles that are disjoint. No point lies in two obstacles. But now, after extending them, they can happily intersect with each other. And I need to generate a free space. I want to divide the plane into trapezoids so that there is two regions between the trapezoids. They are only in the free space points where the robot doesn't intersect any of the obstacles. So for this, I need the union of these extended polygons. Take C1, all the points that belongs to. Let's see an example. Here is obstacle P1, P2, and here is my robot. Just a disk. What is minus R? It's still a disk. What is the Minkovski sum of P1 intersected with minus R? I kind of smoothed the boundary of this triangle. And the same goes for this one. Except that now there is intersections between these two regions, the fact that they were used to being non-intersecting. Doesn't influence right now. I want to ask, what is the region? Let me exaggerate it a bit. For the sake of the video, so this will be more like this. So now is a region, it's an overlap. I want to create a map of the plane so that I know here I'm outside, here I'm inside one of the obstacles. I need to compute the union, and the boundary of the union here will be this is outer boundary. So compute the union. If the center of your robot is outside this union, can you graph Q if you want to generate it in LaTeX? If the center of the robot is outside the union, then the robot is completely in the phase space. The robot does not intersect any of the obstacles. If my disk robot is inside this boundary, then I intersect at least one of the obstacles, possibly both of them, but I don't care. Intersecting with one is bad enough. Okay, so I need to compute a union. We'll talk about it. Now I have the union. I'll do the same vertical decomposition that we saw earlier. Just partition the plane into trapezoid. Remember, from every vertex, shoot rays ups and down. And create the graph of every two trapezoids that are near each other are connected, and find a path. Okay, and sometimes I'll denote this union of obstacles by just, you're familiar with sigma. Here I'm using the a union from 1 to n. This was a shorthand of all the CIs.
Why do we need to do negative R?
That goes back to this proof that if my robot, if my translation brings the robot, so it has an intersection with Q, then when I'm writing what is this translation, it's a point, some point in the obstacle minus some point in the robot. So plus minus a point in the robot. Then these translations belong to P, Minkovski sum with minus R. It's just from this algebra over here, nothing depending. Okay, that's the algorithm so far. Now let's start to talk about what is the complexity of this union. It's going to be the bottleneck of the whole spiel. How many vertices are in the union of all the obstacles? So let's ask, what is the maximum complexity of the union of n triangles? Let's assume that the triangles are disjoint. Sorry, n triangles. These are disjoint, and we know what's the complexity. Triangles do intersect. And the complexity, I will remind you again, how many vertices, edges, holes, because of Euler, if you bound one of them, you kind of bound everything. Complexity is like the maximum, when you are generating the DCL data structure for this region, this union, what will take the maximum amount? That's what I cared about the complexity. So people, help. What's the maximum complexity of n triangles? Do whatever you want with them.
Just n.
That's minimum complexity. They have 3 n vertices. N triangles have 3 n vertices, so that's like the minimum complexity. What's the maximum?
3.
No, they don't have to be disjoint. They can happily overlap. That's a fantastic question for the exam because you had similar question in the homework too. Take a set of triangles, do whatever you want with them, but generate as many vertices as possible. They are not necessarily obstacles, they are not pseudo-disks, which we'll define in a moment. Of course, order of. Here I do half of my triangles. And to create the maximum complexity, to create as many vertices as possible, I'll take the other ones to be this one, another one, another one, and so on. So this is n half. You had a similar question in the homework too about intersection of two paths, about intersection of paths that are not x monotone or y monotone. So here I don't assume anything about these triangles, and you see that every horizontal and every vertical triangle, what does it do? What is the free space of all these triangles? Or what is the union? Well, the free space is everything outside, both red and black. The free space consists of a lot of holes. There is a hole. If my robot is somewhere inside this hole, it can move without hitting any triangle, but once I hit the boundary of this green hole, I hit one of the triangles. Same goes here. So altogether, how many vertices did I generate? Obviously, I generated up to a constant, the maximum possible, which is theta of n squared. So the union of n triangles can have quadratic complexity. But there is a miracle that's going to appear when we talk about the free space of our robot. Because my original obstacles are disjoint. My original obstacles are disjoint, and they are all convex, and the robot is convex. So even when I get them to be fatter, those are Minkovski sum, replacing the triangle that was here earlier. I had these two triangles, and I computed the Minkovski sum with the disks, so it was these fettered shapes, and they start intersecting. But I want to say that it still cannot be as bad as this case. So let's prove it. So we're going to concentrate for a while on the union of objects, and let me ask you what is a pseudo-disk. Well, there is no such thing as a pseudo-disk. We don't even try to define a single object and to look at a single object and say this is a pseudo-disk or not. But when I look at two of them, I can ask, do they intersect as pseudo-disks or not? So what's the difference between disks versus ellipses? I can take two ellipses and take from one, remove the second one, and break my shape into two pieces. Ellipses can do it. Disk cannot. If I take a disk and remove another disk, then whatever is left is connected. I'll take one object and remove the other one. I want it to still be connected. You can eliminate it already, of course. You can completely erase it, but you cannot split it into two objects. Another way to ask about it is here is one shape. Again, I cannot ask, is this a pseudo-disk by itself? It's a meaningless question. But I can ask, is this shape and this other shape do they intersect as pseudo-disks? If I take the black minus the red, am I left with one connected component or two or more connected components? In this case, when I remove the red, I'm left with something that is connected. If I ask about the green and black, then they are not pseudo-disks. Removing the green will disconnect these two portions. You can also think about it by counting intersection points of the boundaries. Count how many intersection points there are on the boundaries. I remind you this notation, partial, this partial D, is the boundary of the first shape, the skin of the disk, the circle, which is the skin of the disk. This will be the skin of the other disk. How many intersection points do they have, if any? Possibly 0, one is fully contained, or they are disjoint. Possibly 2, it must be an even number, by the way. But what happens here? 4 intersection points, in the case of non-pseudo-disk. Same goes here. 4 intersection points of the boundaries versus 2. And where is this name coming from? Well, obviously disks are pseudo-disks. 2 disks are pseudo-disks. But it can be very arbitrarily complex shapes, and I can still say, here is a system of pseudo-disks. Every pair of them intersect in the boundaries of every pair intersect in 2 points.
Well, could it intersect with just 1 point?
It doesn't make anything interesting if it's just tangent. Then I think about it as 0 point or 2 points. So yeah, I dodge this question exactly. I need to address, I'll say that if they tangents, then I just erase them. I don't count. They don't cross. Okay, here's a little observation. You have 2 convex shapes, P and Q. Minkowski sum is on hold for a moment. I have 2 shapes, P and Q, and they are disjoint, no common intersection. And I'm walking around the set of all directions, and I want to ask for each possible direction. Remember, it asks for each possible direction. I'll generate a line in this direction and ask what is the last point that you intersect. And is the point that you intersect is from P or from Q, for the most extreme points that you have. So I'll paint every point on the circle of direction as pink if it's coming from the pink shape, and gray if it's coming from the gray shape. What does the circle of direction looks like if these 2 are convex? So as I'm rotating my extreme points direction, then for a while I have only points from Q that are coming from this direction, only point from Q, until I hit the common tangent, one of the 4 common tangents. And from now on, I only have points from P coming over here, that will be the extreme point, until I hit the other direction of the other common tangent, right here. And from now on, I'm just taking parts from Q. So in particular, things that cannot happen when I paint the circle of direction is that in the circle of direction, you will have, I don't have pink, but if this is P and a blue will be Q, P and Q, then what I cannot have on the circle of direction is that I have some extreme points from P up here, and another extreme points from P up here, and extreme points of direction at which Q is extreme here and here. Of course, it can happily happen if my object A intersect and B's are not pseudo-disks. Correct? If P and Q looks like this, P and Q, then obviously here is direction where I have extreme points from one shape, direction from which I have extreme points from the other, one, another, and they can intersect happily many, many times. But if they are disjoint and convex, basically, if there are disjoint, it cannot happen. Hopefully, everybody agrees with me? I don't say anything controversial here. Okay, let's put things together. I still have the robot. Convex, happy. I have two obstacles. P and Q are obstacles, they are disjoint and are convex. And I considered P Minkovski sum is R, should be minus R, but didn't want to make these slides too complicated. And the other obstacle, P2, which is Q Minkovski sum with the very same robot. Before I continue, let me try to give you a gist of where I'm going with this proof. With this theorem. Let's think about two segments, S1 and S2, two segments, and I want to compute the Minkowski sum with a disk. My robot is just a disk. What is the Minkowski sum of S2 with this disk? Something like this. What is the Minkowski sum of S1 with this disk? Something like this. And that's possibly the output. And that doesn't look surprising, but remember, the segments cannot intersect. So what the robot cannot do when I start drawing this region, it cannot change its size. So in particular, what I don't expect to see from the Minkowski sum of this creature is that the Minkowski sum of S2 will somehow stab the whole Minkowski sum of S1 and go all the way and penetrate to the other side. Somehow, because the segments are disjoint, then this fattening region might intersect, they might have points in common, but they cannot one shutter go all the way into the other and separate it into two pieces. So that's exactly what I want to prove here. So P and Q, example, P and Q, two separate objects, disjoint, convex, happy. No points in common. You're computing the Minkowski sum of both of them with the robot. I don't have the image of the robot here. But it's the same robot, it's the same size. If you don't like this general robot, think about the disk. It behaves the same way. And what do I want to convince you? That these two shapes, C1 and C2, are pseudo-disks. Claim C1 and C2 are pseudo-disks. They can intersect each other, but one cannot shatter the other one. Consider C1 and C2. But I want to say that this is a pair of pseudo-disks. In their boundaries are at most two intersection points. Assume not. Assume that C1 minus C2 looks like this. That is, once I remove C2 from C1, I'll partition C1 into two pieces. Assume by contradiction. I want to convince you that it doesn't happen. Okay. Let's do our trick of computing the extreme points. I'm going around the Minkowski sum of both shapes and compute the extreme points. How will it look like? In this figure, if I look at the extreme point in this direction, it's green. This direction, it's extreme point in this direction, it's green. Green, green. Going upward, it's purple, blue. The same when it goes down. That is, when I go in the extreme direction of the extreme point, you'll have blue, green, blue, green. But how could it happen? It will mean that the original shapes have the property that as I'm looking at the extreme point of the original shape, I'll have a blue, green, blue, green. Which the previous slide said, that cannot happen. Before the Minkowski sum, I cannot have extreme points that alternate. There is only two intervals. One is fully green, blue, gray, That is how it will be folded. Circular direction, there was one region that corresponds to the one of the shapes, and then another region that corresponds to the other one. I did not have any purple in the middle or the green over here. So it cannot happen that they alternate after computing the Minkovski sum. Why? Because the Minkovski sum just takes the extreme points in each direction. If the extreme points of the union comes from the green, it means that there is a green point of this polygon, which is to the right of the extreme point of this polygon. And the same goes in this direction. And going down, it must be an extreme point of P, which is higher than the extreme point of Q. So why doesn't it happen in this example? Because in this example, in this example, the highest point will be, so I have a region that comes only from the green, and then I'll switch into a region that comes only from the blue. Okay. So hopefully everybody is happy. After this region, the Minkovski sum is every polygon is every two obstacles. Minkovski sum is a robot are pseudo-disks. Great, who cares? Why do I do all of it? Because I want to tell you something about the union of all of them. So when I'm computing the union of the shapes, I want to ask how many vertices do I have on the boundary of the two shapes. There are points that are only in red or only in blue or in both. I get both points that are in neither, and the boundary of moving from being outside both to being inside at least one. If I have two polygons, how complicated could their union be? If it's arbitrary polygons, could be n squared. Again, my examples all over the place today from comb that comes from here and comb that comes from here and creates n squared many intersections. But if there are convex, then if there are convex and or even they are not convex, assume that we prove that we will prove that the union only have order n many vertices. Not n squared, we are down to only linear number of vertices, assuming that every pair intersect as pseudo-disks. Either don't intersect at all, or touch but only create two vertices, and so on. Why do we care about this bound? Because if I tell you that the union only have order n vertices, do a line sweep and try to compute the union. Do a line sweep and try to compute the union. Now, I'm only computing the union of two shapes. Maybe very complicated shapes, but only two shapes. What are the events of the line sweep? Possibly I hit a vertex of one polygon. Possibly I hit a vertex of another polygon. These are all unions. These are all events that where a segment ends and a segment starts. Just based to the line sweep. But I have another type of event, intersection of two edges of one comes from this shape, one comes from the other shape. But if you know that the number of these events, every such event, is an event on the union, every intersection is an intersection of the union, and I'll tell you that the union has only linear many vertices, then the number of events is only n, so each event is handling log n time, so the overall running time will be n log n. That's cool, but why does it? And a key observation that when I saw it first I found very confusing is that if I have an intersection between the boundary, then this vertex must be on the union of these two objects. If you have any segment that is the intersection of the two objects, it must be also a vertex of the union. How come? Because this vertex is, if I move from the blue barely outside, I'll be in the white. I'll be outside the blue. If I move from the red a bit downward, I'll be again in the white. So any intersection between the two must be a vertex of the union. Once you told me how many vertices are in the union, you told me how much time the line will take. Okay. Moving along. Let's assume that was for two objects. Now, let's assume that I have k polygons, convex, but each pair behaves like a pseudo-disk, or at most two intersections. And let n be the total number of vertices at each one of the polygons. I want to convince you that the total number of intersection points, vertices of the union, is at most m. And so it should be 2m. Most 2m. That's what we need to fix. Remember, as opposed to the case of two sets of triangles that cross each other and do all over the place, creating n squared. Now I will say, if you tell me how many vertices the polygons have to start with, the obstacles, the flattened obstacles, then the number of vertices on the unions is not more than the number of vertices of the original polygons. So let's prove it. And we are using here a cute example of charging scheme. I'm going to put dollars, and then I'm going to transfer these dollars between different candidates, and I'm going to show you that I never overdraft. I never had a vertex that I can't pay for. And my budget will only be 2m many dollars. So how do I arrange it? I'll put 2 coins of $2, 2 coins of each, $1 each, on each vertex of any of the polygons. $2 here, $2 here, $2 on this vertex. These are vertices of the original polygons. Now I'm going to start to shift. How many dollars did I spend? Well, if my original polygons have only m many vertices, it cost me so far 2m many dollars. And I want to convince you that now I can shift the dollars so every vertex, either of the union, or either of the original polygon or vertex of the union, has somebody to pay for, has at least $1 inside it. So let's compare it to the case of triangles. So it's easier to think at the same time what goes on in the set of triangles. Triangles, I'm trying to do the same thing. I put $2 right here in each vertex, $2. $2. And I want to show what is my charging scheme. There are new vertices, vertices of the union, vertices that are intersection of two separate objects, and somebody needs to pay for their existence. How do I find somebody that will pay for the existence of V here? V is a very new vertex. It lies on the intersection of one object and another object. And I don't know why the objects don't appear. So, so assume that V is a vertex of the union, and what I'm going to do from there is to start walking along. I'll pick one of the edges that defines it. One edge is E, one edge is F, belongs to two different obstacles. And I'll pick one of these two edges, let's say F, and I'll start walking inward F until something happens. Either, another slide. I'll get back to original, to another slide. So I'm walking along this edge until something interesting happens. What can happen? Possibly I will get out of this edge, which continue all the way out, in which case I'm in trouble. Or, in this figure, I'm happy because before I'm getting to the end of F, I find a rich person. This vertex have $2 to start with. Take this dollar and give it to V. Now, am I done with this? Is this vertex out of the woods? Not really, because there is another guy over here, W, or U over here, and I'll keep walking along this edge until I hit W, take the other extra dollar, put it on this vertex, and I have somebody to pay for it. Okay? I mean, this experiment might go wrong if I pick the wrong edge. What happens if I pick E? If I pick E, I want to charge this vertex to the endpoints of E, but I'm in trouble because I reached the other endpoints of E before hitting anybody that is vertex of the original polygon. That's something that can happen, or happily here. But either this direction is good or this direction is good. Why? Because of pseudo-disks. But if the endpoints, if you were in a scenario at which here is E, here is F, and if I'm in a scenario that starting from V, I will go out, but then I'm out of, let's call this one P, let's call this one Q. Start from V and hitting another endpoint before hitting the endpoint of P, and at the same time going along this edge and not hitting the endpoint of this edge before finding a vertex to charge for V. Well, this cannot happen when there are pseudo-disks. It will happen in the triangles over here. But here, since they are pseudo-disks and they are polygons, then look at the intersection of two objects. When this is the intersection of two convex polygons, look at their intersections. There must be a vertex of at least one of the polygons on the intersection. Everybody agrees? There must be a vertex of the original polygon inside there that is bound on the boundary of the intersection. Right? As opposed to the case of circles, this cannot be a straight segment, and at the same time, the other polygon will give me a straight segment. Right? For polygons will not do anything like taking this edge, making it hit the other polygon without having a vertex on this other edge. So we are happy with this very wild hand wave. There is always somebody to charge, so altogether there is only n vertices. You'll have to stare at it a bit, but it's true. Okay, how does it help us make a solid algorithm from the whole thing? Let's see what happens. I assume that my robot has m edges, and I'm given P as one obstacle, a lot of obstacles, and I don't care. I'll triangulate it no matter what, and I'll triangulate it into n triangles. Every polygon you can triangulate. Remember, ear chopping, for the midterm. Ear chopping, you can always find a code that cuts a polygon. We know that every polygon can be triangulated. So I'll take all the obstacles and triangulate each one of them. From now on, every obstacle is just a triangle, which is convex, by the way. Compute the robot plus T, the robot Minkovski sum, with the last obstacle. And now I want to compute their union. How do I compute the reunion? That's a point at which you can say this course also helps for 45, because it's an excellent example of divide and conquer. What do I do? I'll think about all my polygons. not a pseudo-disk, so I'll do it again. So I have 4 enlarged polygons here. R plus T1, R plus T2, all the way to R plus Tn. These 4 regions, which are heavily intersected. What do? I think about, let's give them names, C1, C2, C3, and C4. And what do? In my first iteration, I just do, how does merge sort work? You take an array, split it into 2 halves, split it into 2 halves until you are left with an array that contains only 2 elements. And then you sort every pair of elements. And then you have a sequence of sorted items and another sequence of sorted items, and you merge them into a sequence which is twice as long. So you merge pairs into 4 tuples. Then you merge 4 tuples into 8 tuples. Merge 8 tuples into 16 tuples, and so on. What would I do here? I'll divide them into pairs. For example, I'll think about the pair. For the camera, I should take a different color. Compute C1 union with C2. The union of C1 and C2, which are nothing but this plus this. Great. Now compute the union of the other pair. Compute the union of C4 and C3, which is this region. How do I compute the union? Just doing a line sweep. Just doing a line sweep. How much time do you spend? Linear in the number of obstacles so far, times log n pairs sorting in each event that we are handling. But you generated a lot of vertices, including vertices that will vanish later on. But still, every pass of the line sweep only takes n log n time. Now I have shapes that are the union of pairs. Now merge the blue shapes with the red shapes. Do another pass. Now you're merging 4 into 4. Now you're merging pairs into 4 tuples. So you will generate an overall union whose boundary is this creature. So every line sweep costs the number of vertices, which is n, times log n. And how many passes do I need to do? I had pairs, 4 tuples, 8 tuples, 16 tuples. After log n many tuples, I merge everything. Wow. And now I have these shapes, and I do vertical decomposition and do the graph, and I'm done. Well, and again, all have, and I'll just do vertical decomposition. And what are you finding exactly? We are finding a path of the center of the robot in the free space. Because the path of the center of the robot is in the free space, the robot itself doesn't have any point in the intersection. Fantastic. I'll get to this slide in the next lecture about what happens in higher dimension, which is an interesting case. Let's go back to 2 dimension, ask what happens if I want to find the shortest path. If I want to find the shortest path, not just a path of the robot, I want to, this path looks something like this. And is a path that has the shortest level outside all the obstacles. And look at the pieces of the shortest path. And it's a theorem that says, think about it as a rope. And now I start pulling this rope from both sides until this rope becomes taut. It's not necessarily a straight line. Maybe it is, but possibly it's not, depending on my obstacles. So it needs to bend from place to place. But every point that it bends, it touches one of the obstacles. It might be either the original obstacles or the obstacles with the Minkovski sum, I don't care. So every edge of the shortest path is also an edge of the visibility graph. What is a visibility graph? We already saw one example of the visibility graph when it talked about the art gallery. Let's be a bit more formal. The visibility graph will consist of the vertices of the visibility graph are all the pairs of vertices of the original polygons. It could, of the original obstacles. It could be two obstacles of two vertices of different obstacle, or two obstacles of two vertices of the same obstacle. It's also in the visibility graph. However, what makes an edge belongs to the visibility graph. It needs to be between two vertices that see each other. Two vertices that see each other. Where do I have vertices that don't see each other? Well, this vertex and this vertex don't see each other. If I draw a segment between them, it will cut into one of the obstacles. See each other meaning there is nobody that hides them to such vertices. So create all this graph. It could happily have n square many vertices, many edges, sorry, every pair and every pair. But once I compute this visibility graph, my problem is very easy. I need to measure the length of every edge, see how long is it geometrically, that's the weight of the edge. And what do? One Dijkstra. Dijkstra is happy to take a graph. It's not a planar graph, but Dijkstra is happy to take a graph with positive weights on its edges and tell you what is the shortest path from S to T. And what I just hopefully convinced you, or you're just way too tired to complain, is that the shortest path consists only of pieces of vertices that see each other. That is, again, it's a trick of moving from some continuous infinite domain into a domain where we only need to check discrete many variables, only n square many pairs that might see each other. So my problem is just how to compute the visibility graph now. So let's get to computing the visibility graph. So pick one of the endpoints of one of the segments. Let's think about Q. And I want to sort the other vertices in the order that they appear, but called circular. Like if I'm rotating array, which vertex do I hit? So let's do it. I sorted them, either robustly or non-robustly. And now I'm going to do circular sweep. What is circular sweep? Q is one of the vertices. I just meditate on Q over here, and I sweep the plane with, not a line, but with a ray. And this ray is going to sweep the plane by rotating from here to here, doing a full 360 degrees around Q. It has events, like just normal line sweep. What are the events? When I start hitting a vertex of any of the segments, or when I stop hitting a vertex of any of the other segments. This will be an event. I saw them beforehand, so I know how many do I have. You'll see this example also. I keep the status. What is the status? What are the segments that you intersect? What is the segment that the line sweep intersect at every moment? Right now my line sweeping ray intersects this guy and this guy and this guy. How does the status store this segment? They store them all sorted in what order? They store it sorted, status sort the segments in the order that they appeared along this way. Just like normal line sweep. How do I know if Q sees a vertex? It needs to be the closest to it, not occluded by any other segments. So in the status, it needs to be just the lowermost, the minimum segment in the status that just started or ended, and that will be my hint to insert this vertex into the visibility graph. Let's admire this wonderful animation once again. It was a dense lecture. I just let it leave traces on the segment that is always the closest to Q for each angle. So you see the events where I jump from here to here. Oh, that means that this endpoint is seen by Q. This endpoint is seen by Q. What about this endpoint? It creates an event, but this event of this segment is not the closest to Q on the status, so I don't care. It's only the lowermost segment that I care for, so I can compute in n log n the endpoint that Q sees. Do it for any other endpoint of any other segment, altogether n squared log n. You have your graph, compute now the path of the robot, you're done.
Very good. Let's go. Next talk we'll mention a bit, we'll go over it, and we'll talk about how do you do with robots that are also rotating or have joints or do other things, more degrees of freedom than just two.
Thank you.